think everybody bar James, you and me is muted at the moment, and I think I'm just about to mute James. Bye, James. We're webinar here. I'm Andy Clark. I'm the chair of the Northeast branch of the Energy Institute, and I'm here to introduce Ross Winter, who's done all the work on this. He's done all the arrangements about getting the webinar to fit. He's written the webinar. He's got it promoted. He's got it going in there. So this is entirely his pigeon, and he deserves a lot of credit for that. And the clapping is not going to work very well over the internet. So take it you're being clapped, Ross.
That's fair. I'll clap myself.
Ross has spent some time down in the Antarctic and has been talking about energy use down there in the sub-zero temperatures. And this is partially a follow-on from his wife, Kate, who I think is also online with us. And one she did, and I missed it. Therefore, I demanded we had a repeat. And then this COVID-19 came in and rather threw us all off our tracks. But Ross, being determined, tried to make sure that we would still keep to the pattern of having a webinar, having a meeting on the early Tuesdays of the month, and it's here. If this works well, we'll try and get some more in and do it on there. So with no more ado, Ross, over to you.
Hey, thank you very much, Andy. So just a bit of housekeeping just before we start. I think everyone should be on mute, and if you can try and keep your videos off, that'd be great as well. There will be time for questions at the end. There's a chat function on the system which you can use. If you want to put questions in there or save your question at the end, we can unmute you and you can ask your question, and I'll try and answer as best I can. So let's see if the slides work. Okay, so thank you, Andy, for that introduction. So as Andy says, my name is Ross Winter. I'm on part of the committee in the Northeast Energy Institute. So I'm chair of the Young Professional Network. And so today I'm going to be talking to you about energy use in extreme environments with Antarctica as a case study. So just a quick outline of what we're going to talk about today. I'll give you a brief history of Antarctica. I'll give you some pub quiz facts, because I know with this lockdown, lots of people are doing pub quizzes, so get you some more nuggets of information there for you. I'll talk a bit about what research stations there are and what work's going on in Antarctica, and then I'll focus on the zero emissions research station that I visited in January and February, and then I'll round up with my thoughts on the future of energy in Antarctica. As most people think when they hear Antarctica, the first thing they think of is penguins. Unfortunately, this picture here is the only time you're going to hear about penguins today. So, just to give you a brief history of what we know about Antarctica. Antarctica itself has not been explored much until about 100 years ago. However, it was hypothesized by as early as the ancient Greeks. They knew about the Arctic and they thought there must be something opposite, the Antarctic. But the first time really Antarctica was on maps was in about the 1700s. And as you can see on the map on the screen, there's no continent there. They hadn't seen the continent of Antarctica, but they knew there must be something down there. And then fast forward to the early 1900s, when we had the first real exploration of the pole. This was due, the continent, sorry. This was due to ships being able to get closer and adventurous. So this map here is from Shackleton's trans-Antarctic expedition. So it was just after Scott and Amundsen had reached the pole, and Shackleton a couple of years before had failed just short of the pole as well. And as you can see by the maps from then, you can sort of see the shape of what Antarctica is as we know it today. Then we jump forward to the 50s. Now, the understanding of how Antarctica looks is a lot closer to what it is today. It's still not quite right, but the reason why we started to get a lot more focus in the 50s was when we had the International Geophysical Year, where they really focus on pushing Antarctic science. And as with most places, as soon as people started to understand what it looked like, they tried to claim it. They tried to take territorial claims of the continent. So early on, there was a few nations, the UK included, which tried to take some sectors in Antarctica. There's a few Northern Hemisphere ones which you might not think has a direct claim, but a few of the southern hemispheres like Australia, New Zealand, and the South American nations as well, who are obviously a lot closer to the continent. But who actually owns Antarctica? Well, no one is the answer. Since 1959, there's been a document called the Antarctic Treaty, which is signed by 12 nations initially, which was designed to preserve Antarctica for peaceful and scientific endeavours. And that, at that time, all territorial claims were set aside. You can see there just a list of the 12 countries which were their initial signatories on that. That original Antarctic Treaty ran until 1991, and that was renewed when there was 34 new signatories added to it. And that treaty is still running now, and it runs until 2041. So we're 20 years away from the end of that, but there will start to be changes coming up and what people are wanting to do with it after that point. So, just some facts on Antarctica. Firstly, the size. People sometimes don't really understand the size, and that's due to the maps which we have. So as you can see here on the map, as most maps, Antarctica just sort of peeks onto the bottom of the map. You're not sure, is it big, is it small, what's happening there? So, to put it into context, Antarctica is larger than the United States, the mainland United States. It's also bigger than Europe, land mass combined. It's bigger than Australia, so it's a fairly sizable continent which we've got down there. So here's another image of it, and you can see it's quite a remote. It's a very remote continent. There's usually only 3 ways which you fly into the continent. There's the African way through Cape Town into the east of Antarctica. The Americans going through New Zealand also into the east. And then the other access through the peninsula is through either South America or, as the British quite often do, through the Falkland Islands. Obviously, with owning territory there, it's sometimes it's more convenient for them to fly through their own territories. So Antarctica itself is the coldest, the windiest, the driest, and the least populated continent on Earth. On the east Antarctica, so Antarctica is split east and west, roughly down. There's a mountain ridge called the Trans-Antarctic Mountains, and usually the larger side on the right of this image here is East Antarctica, and then on the left we've got the West Antarctica. So in East Antarctica, temperatures are on average minus 40 degrees C. There is a variation, of course, with that. The coastal areas are warmer, and the interiors are obviously a lot colder. I think when the lowest temperature recorded is about minus 80 to minus 90 degrees C, so it can get pretty cold down there. On average, there's less than 50 millimeters of precipitation a year, so that generally falls as snow. And with that small amount of precipitation is classed as a desert. In East Antarctica, the thickest ice is 4.7 kilometers thick, and on average on the ice sheets it's about 2 to 2.5 kilometers thick. So we've got a lot of ice and a lot of water tied up there. And as well, it's very windy. Wind speeds can reach up to 200 miles an hour and consistently at 200 miles an hour. So it's quite a harsh and a hostile place to live and work. So why do people want to work or visit Antarctica? Well, there's 3 types of people who visit Antarctica generally. There's scientists, explorers, and engineers. So every year, more than 4,000 scientists visit Antarctica around the various bases. And they're looking at a variety of things. You've got natural landscapes, history of the Earth, how people cope in the environment, how sort of world changes, so they can look at ice cores for measurements. And some of the images here are just some of what we've got at the moment. On the bottom left, you've got the science, the medics, who look at how people survive in isolation. That is very transferable to a lot of the space travel which is being touted around, the travels to Mars, and how human bodies cope to the darkness and isolation. The middle picture there is meteorite scientists. Antarctica is one of the best places in the world to find meteorites. It's generally white or a blue for the ice, but the rocks are usually dark and black. So it's very easy to easy to see on the ice. And the image in the bottom right there is taken from something which you might have seen in the news in the last couple of days. It's the new models on the ice loss or gains around Antarctica. So in the red colours there, you can see that there's a lot of ice loss, and the blues are the ice gains. So you can see that Antarctica is melting, and this is important because it's about 60 metres worth of sea level rise if Antarctica melted. So there's a lot of it's keenly studied to make sure that Antarctica is not melting too quickly. But it's not just scientists who visit Antarctica. There's explorers who, obviously back in the early 1900s, were in the race to the pole, but also there's lots of different people adventuring in Antarctica. And then there's the engineers as well. So as I mentioned, there's quite a lot of research stations in Antarctica, and they need to be run by people. So where are these research stations? Well, this image here shows where the majority of them are. This is not a full encompassing of all the stations, but it's a lot of them. The one thing that should jump at you straight away is that the stations tend to be around the coast, and that's purely for the accessibility. It's very hard to get inland in Antarctica, so there's no roads. Air travel is very hard. So a lot of, or if it is, it's quite expensive. So a lot of the supplies are shipped in. So being near the coast makes it a lot easier to transfer it from the ships to the stations. Of course, the Americans have gone and plonked one of their bases right on the South Pole, because that's what the Americans like to do. They say we own the South Pole, not that they do. So I'm going to quickly take you through a couple of the research stations around the continent. I've just highlighted them here on the map. So I'll look at the two British bases, and I'll compare it to some of the New Zealand base, the American base, the South Korean base, which is a lot newer, and then I'll end up talking about the Belgian Princess Elisabeth station. So the main British research station is Rothera. It was built in the 70s. It was built near the site of the original British station, which was built in the 50s. But you can see the occupancy of Rothera is about 100 people during the summer, and that reduces a lot during the winter. But when I say summer and winter, you've got to remember that's different in the southern hemisphere than it is in the northern hemisphere. So their summer season is usually November through to February, because of that's when it's 24 hours of sunlight is during their summer. The occupancy is also greater in the summers months due to the amount of scientists who go there, because they want to work during the sunlight. It's very hard and very harsh to work during the winter months. But there's also benefits of working during the winter months, which I'll come on later. The station itself is powered by diesel generators. There's some solar panels they were put on at the end, but they're not used greatly. But it's diesel generators, the main form of power. As you can see from the image, Rothera is on an island, and there's not much fresh snow there, so they have to get their water through desalination, so reverse osmosis. So that's taking the seawater, the salty seawater, and change it into fresh water for drinking. They do use the salt water for some of the plumbing through their toilet systems, etc. But they need to use a very power-intensive way to get their fresh water. As you can see from the image as well, right at the bottom, this was taken during the season just past. They are currently building the new wharf at Rothera, and that's going to be able to dock the Sir David Attenborough, the new research vessel, which you've heard in the news the last couple of years, with its submersible boating with Boatface. The other British station is the Halley research station. This was built in the 50s. The current one is now Halley 6, so this wasn't built in the 50s, the one you can see in the image. It'd be very forward-thinking, futuristic design if you think that's what they built in the 50s. The occupancy there is a lot smaller in the summer as well, and there is a overwintering staff there usually, but the last couple of years they've had to stop running during the winter, which I'll come on to in a second. What you might remember Halley for, one of the most famous things for it, is the discovery of the ozone hole. So they did all the monitoring and the research to discover that there was a hole in the ozone over the Antarctic continent. As you can imagine, as you can see as well, there's not very many renewable powers. There's powered by diesel generators, which use a combined heat and power plant. And the excess heat, which is used once for heating the station, then gets used for melting the snow for their drinking water. But you'll see from the image that the station itself is built on stilts with skis, and that was part of the design because in the last couple of years, Halley has been moved location. Because in the wisdom for the British, they decided that they build the station on floating ice, not grounded ice. So as with natural processes, the ice slowly moves out towards sea and breaks off. So what they've been monitoring is this chasm 1 in early or late 2012 started to open up or start to increase the size, and they're worried that that was going to make a big crack along the ice shelf, and the whole ice shelf would break off and float away, and they'd lose the station. So over a couple of years, they planned and they've moved Halley to their new site, which is 23 kilometres upstream in the ice stream. However, after they've moved it as well, they discovered in 2017 that there's this new crack which was forming on the other side, called the Halloween crack. So there's danger. They're worried that that might develop, and that's why no one is currently working there over the winter, because mounting a rescue if anything happened is very difficult in the harsher conditions during the winter. So just as a quick summary of how Halley's developed through the years, looking from the original. So when it was built in the 1950s, as you can see, it was timber structures. These were very thermally inefficient buildings, but that was how they've been building structures in Antarctica right back to when you read the stories of Scott and Shackleton, and they were living in timber huts on the continent. But as you can see, progressively over time, the snow drifted and started to bury the building. So after 10 years, they built a new version of Halley on the same kind of design, timber structures. Obviously, you think the technologies and the knowledge of what goes on there has improved, so there'll be a bit more thermal efficiency. But again, you can see slowly over time that the structures were covered with blown snow. So that changed their design for the third version of Halley, which was a sort of a tube itself, which they designed to be covered by blown snow and be submerged. As you can see here, it's coming to its end of its life at the edge of the ice stream and being melted out into the southern oceans. And again, that design worked, so they wanted to do that again for their next version, Halley 4. But you've got to remember that even though you've got the thermal insulation from the snow covering you, you then remember there's no natural light when you're living in the station, so it's going to be quite hard living in the station in those conditions. So eventually they decided that living underground was not the way to go. They went for Halley 5, they went to the more stilted design, which you see is pushed on to Halley 6 as well. So the idea of this, they were taking it off the ice, you're not losing any thermal heat down through the station into the ice, and the snow and the wind can blow under and not accumulate as quickly. However, it was designed on stilts which can raise and lower, hydraulic jacks. Eventually, over time, snow did start to accumulate and they couldn't raise it any higher, so they were worried that it was going to be buried. And that's what influenced the Halley 6. So they put it on skis with the same idea. It's on hydraulic jacks so it can raise and lower, and then it's on skis so when it gets too much they can move it to a new location. So moving away from the British to some other bases, the New Zealand base, this was the Scott base, which was built in the 50s. It was back in the International Geophysical Year. It's got a similar capacity to Rotherham Station, the British Rotherham Station, but they've shown that they can upgrade their facilities. So when this was built, again, it was built with diesel generators as a reliable technology back then. But in 2010, they installed 3.33 megawatt wind turbines next to the station, so producing just under a megawatt worth of capacity of power. And when it was installed, Scott Base had a 150 kilowatt load. So As you can see by those numbers, there was a lot more power available than they actually needed. So they export that to the nearby American McMurdo base. So talking about the Americans, McMurdo, I wouldn't really call this a base. This is more Antarctic city. It's probably the only Antarctic city there is. There's a bus service there. There's ATMs. There's a fire department. And that's because there's just so many people there. There's over 1,000 people there during the summer. So this is by far the biggest and the busiest base, which is in Antarctica. Again, it was built in the 50s, again with diesel generators. But during the 60s, they tried to have, they installed a nuclear generator there. So all their power was coming from nuclear power. I'm not sure if that's maybe the best idea with the Antarctic Treaty and what you're going to do with the nuclear waste, but that's what the Americans decided to do. However, after the 10 years, they decommissioned that and they went back to the conventional diesel generating, as well as the importing some of the wind power, excess wind power that the New Zealanders make. Again, both those stations run on water desalination to get their water. So looking now, moving away from the older bases from the 50s, one of the more recent bases is the Jang station, which is built by the South Koreans. So this is built in 2014. It's got a smaller, similar occupancy to places like Rothera and Scott Base. However, despite what they can learn from the Scott Base, so for other bases, they've gone with conventional diesel generation. As you might see in one of the outbuildings on the top left there, there is some solar panels they've put in, but generally their main power source is diesel generation. So they've not embraced any of the new technologies, especially with you'd expect with South Korea as one of the technology leaders in a lot of these fields. So what you can see from there is like a lot of the research stations in Antarctica are old. They were built during the geophysical campaign in sort of the 50s and the early 60s, so they're older stations. And obviously with these built, they're thermally inefficient and they rely on diesel power. But it's not just the old stations which are like that. Modern stations, they're obviously a lot more thermally efficient. They've got a lot more energy credentials. But again, they're still powered by traditional, also say reliable technology, what they believe is reliable technology. One of the challenges you can see is also the mindset of what people have. This is a quote by one of the engineers from the British Antarctic Survey. During the design stage of Halley, they were looking at putting solar panels on Halley, but they're saying, well, during winter, you've got 105 days of darkness in the year. Well, in the summer, when you're busier, you've got at least 105 days of sunlight, and it's 24 hours of sunlight. So why can't you use the solar during those times and have two sources of power? But at least they are focusing on the energy efficiency of buildings, and that was their main focus. But with a lot of these stations, the renewables are tacked on as an added extra, not part of the core of the design. And with Halley, as with most of these big construction projects, it went over budget. And the first thing which gets knocked off a project when it's going over budget is one of those nice to haves. I'm sure James, who's on this call, I think he might disagree a bit with that, but he's in construction, but that's what the reality is, unfortunately. So just to round this section up, so what are some of the challenges for the renewable energy in Antarctica? Well, weather is one of your biggest challenges. It's cold. It's that cold, concrete doesn't set. And your traditional components freeze, so that your oils and your lubricants used in wind turbines, they freeze. There's no available liquid water, so you can't ship all your concrete, water for your concrete if you want to do foundations in. It's not helpful at all. And as I said, the winds, they're very high, and up to 200 miles an hour, that can destroy wind turbines, can destroy buildings if they're not made properly. And the environment as well is very hard. In the winter, you've got 24 hours worth of darkness, and that can last for 2-3 months on end. So it's very harsh conditions. And as you probably saw from the maps, it's remote. So that means it's very hard to bring in specialists and supplies. That's so mechanical specialists, any supplies you need for fixing things or food, it all has to be brought in beforehand. And there's obviously the biosecurity concerns. You don't want to be bringing sort of alien bacteria into the continent, and because you don't know what's going to happen. and also you've got to adhere to the Antarctic Treaty rules and regulations on leaving the continent as pristine as you found it. But some of these challenges can push it to an opportunity, can translate to an opportunity. So looking at the weather, yes, your temperatures are low, it's cold, but they're consistently low. Very rarely do you get above 0 degrees in the continent. You may have seen, I think it was in February, there was reports that Antarctica was its warmest ever temperature of plus 20 degrees. It's a bit of a misdemeanor because it was on the islands which are in the outer reaches of the Antarctic area. On the continent itself, it very rarely goes above 0 degrees. So you can plan for low temperatures, and it fluctuates, but it doesn't fluctuate a huge amount during the season. Say there's no liquid water. Well, if there's no liquid water, then you can't get corrosion from liquid water, which is also a benefit. And then with the winds, they're predictable. They're high, but they're predictable and they're reliable. And they usually come from the same direction. The Antarctic katabatic winds, they usually come from the centre of the continent out. So you can model them and you can be able to see where the wind's flowing, and you can design buildings and renewable technologies around that. And again, the environment. Let's say there's 24 hours darkness in the winter, or there's 24 hours sunlight in the summer, so you can use that. And being so remote, you've got a very predictable energy demand. No one's just going to turn up off the street and say, oh, can I stay tonight? Before the season starts, they know how many people are going to be coming to each base. They know what science or work they're going to be doing, so they can predict what energy use they're going to be needing for the number of people who are there. And there's limited wildlife. I did say we're going to talk about penguins, but away from the coast, coastal, there's the penguins and some other animals. But as soon as you move inland, there's very limited amount of wildlife. There's an occasional bird here or there. In the time when I was there, I saw probably about 6 birds in 6 weeks. So there's very limited wildlife. So some of the environmental concerns which you have when you're constructing wind farms, etc., in the UK, they're not as much of a hurdle to pass in the continent. So that brings me on to my experience of my trip to the Princess Elisabeth station in Antarctica. It's a Belgian-run station. So here's just some images of it. Straight away, it looks very futuristic design compared to some of the ones which I've shown you already. It's almost, you say it's like a Bond villain's lair sitting on the ridge here. It's got some of the designs you might have seen in previous stations where it's on stilts, so it takes off the ice a bit more. So where is the Princess Elisabeth station? Well, it's 71 degrees south, which is on this northern section of the coast. It's about 200 kilometers inland from the coast. To get there, I had to fly to South Africa, and then you fly from South Africa to a Russian base called Novo, and then there's an internal flight which you take from there to the station. So the station was built in 2007, so it's not one of the newest stations. So they've been around for over 10 years now. When it was originally built, it was had an occupancy of about 16 people. But they've expanded now, and they can take up to probably a maximum of 50 people on site. And during the summer, that's about half of that is scientists. You will notice the winter occupancy is 0. So this is a summer-only station. So they run from the middle of November right through to the end of February. So they've got a few months where they can do all their science in there. So, looking at so here's another image of the station. You can see it on the image here. The first thing which jumps straight into view is there's a lot more wind turbines and solar panels than you've seen on any of the other stations which I've shown you so far. So the station is run on 9 wind turbines, and there's 134 solar panels. That's what they say, but when I was there, they were installing more. There's a running joke actually while you're on the station is if you stand still long enough, they'll put a solar panel on your back. But you can see on the building itself, there's panels on all different orientations, as well as on the ridge there as well. There's also 3 solar thermal panels, and that's how they heat all their water for their showers, and also using it for the snow melt. And for safety purposes, they do have a backup generator on site. So taking a bit of a deeper dive into some of these technologies. So the wind turbines, there's 9 wind turbines. They were built by a company called SD Wind Energy, which is based up in Dumfries in Scotland. So almost as a local company working in Antarctica doing that. The wind turbines, they are designed that they can turn 360 degrees. So whichever way the wind's blowing, they will move and set themselves to that. As you see in the image here, they're all facing one direction here. That is the predominant wind direction, so they don't move too much. They use special polar lubricants, so they don't seize up, or they don't freeze up either. And they are designed that they can be shut down remotely in a big storm, so they don't break as well. They're relatively small wind turbines compared to what some you might see in some big wind farms in the UK. But that means they don't need any proper concrete foundations. So you might be able to see at the bottom of the images, they're drilled into the granite ridge, which the station is based on. So as I've mentioned as well, there's the solar panels. Around the station, you can see me a bit clearer in this image. The solar panels are on all sides of the station, but predominantly the ones on the ridge all are facing north, because that's the strongest direction where the sun is throughout the season while it's there. The sun does rotate around the sky during the 24 hours of sunlight, but predominantly the strongest sun is in the north, and that's where they've put their majority of their solar panels. On the right, you can see just 2 of the 3 thermal solar panels, which they use to heat the hot water for the station. So about 50% of the power comes from the wind turbines, and the other 50% comes from the solar panels. So it's a mix of sources, and that's what they need to make it work. But it's not just the renewable technologies which are used to power the station or to keep the station running. The station itself was designed and modelled to fit the location, and it was built in a passive house structure. As you can see from the CAD image there, in the centre of the building is where the technology core is. That's where all the safety systems are. Then as you move out, you've got your kitchen and your hygiene units, and then you've got your offices and your bedrooms as well in the outer area of the building. There's a ventilation system which circulates the air and keeps it fresh air going through and helps cool it down when need to. Because as you can imagine, the windows are sealed. You can't just crack the window open to help cool itself down, because that would not be great. But the structure itself of the building is designed with 9 layers of. So it's a 9-layer structure. So from the outside to the inside, you've got a stainless steel layer. Then you've got some foam, some sheeting to keep it waterproof. There's a wood layer. Then the biggest section is a large polystyrene, graphite coated polystyrene section in the middle. That's your main insulation. You got some more wood, some paper, and some aluminium foil, which is used as a vapor barrier. Then there's some woolen felt, and then there's also a internal. I suppose there is a 10th layer of the internal wood finish, which you can see from the inside, because having some woolen felt on the inside might not look as appealing as a nice wooden finish. So how does the station itself sort of run itself? There's the station itself in the centre of the building. It's got 200 lead nickel batteries, which basically are used to store any of the excess power which is produced. They're about 80 kilos each. So you imagine trying to get them up the stairs installed in the building. It seemed to be quite an effort to get that sorted. So there's some resistor systems, and the whole building is run on a smart microgrid. So what that system does is it monitors all the available resources, it prioritizes demands, and then allocates the energy to where it's needed. The system itself is run on there's a control center within the station where they can monitor all this as well. But there's also, it can be monitored remotely from Belgium, where their headquarters are. So just in sort of a nutshell, this schematic here shows you how the whole system works. So you've got your energy production on the left, where that comes through to your control systems, where then either goes to battery storage or to demand. And then, as I mentioned, there's a priority system of where the power gets used. So the number one priority is security. As you can imagine, safety and security are our number one priority. If anything happens, you've got to have shelter to keep you warm or to keep you protected from any of the Antarctic weather. Your number two priority is your station operations. So that's your water treatment. So that's sort of your wastewater, your snow melter unit, so to be able to get fresh drinking water. And they also actually treat the water, they retreat the water, and they can use it 1.5 times. So every time the water gets used, they recycle it and then they can use it again where they can. And there's also the ventilation unit to keep the fresh air running in the building. Because it is passive house, it's got to keep that ventilation going. As it's a scientific research station, science is one of the big priorities. Scientists wouldn't be going there if they know that they're going to get bumped off because people want to watch TV. Science takes a big priority. And that's through the lab which they have on site and all the equipment which you use, which I'll talk about it more in a second. And then your lower priorities are things like your daily life. So that's doing washing your clothes or using their entertainment systems or watching films, etc. And you can always tell when it's a windy day or there's a bit high power day is because at the washing machines, there's always a pile up of clothes waiting to be washed because people know there's a lot of water and there's a lot of energy that they can use the washing machine. So with this quite complex and quite a high level, highly complex system, you think there'd be a very complex way of showing this to everyone on site, how the power level is doing, how the water level is doing. Well, it couldn't be any further from the truth. What you have is a pin board, and if there's a high level of water or power, your pin goes in your dark green section. If your water or your powers are running low, it goes into your red section or moves down side. As you can see on just where the pins have been, the water supply doesn't really fluctuate that much. But obviously, as you can imagine, if it's a cloudy day or it's not as much wind, the power can vary a bit. So that helps you focus what you can use or what you can't use. But also, after a while, when you're there, sometimes you don't really need to look at this board because you can look out the window and you can see, oh, it's sunny, it's windy, I think we're going to have enough power there. You adapt to the lifestyle and it works well. Everyone works well for that. But it's not just in the station itself which has this zero emissions credentials. It's even when they go out into the field. So most of the science done at the station is done on day trips from the station, going to places. But on the occasions where they do need to go a bit further afield and stay further afield, they've got these container units, which basically they've strapped on solar panels onto both sides, onto the roof, and that's where that's how they power themselves while they're out in the field. And as you can see, there's a big power demand. This was the science team which I was involved in. Just as after just one day, or actually one afternoon in the field, we didn't go out in the morning, we went in the afternoon. We've got 4 radar batteries, we've got camera batteries, we've got GPS units, we've got power banks, and this is just one science team. There was 4 science teams while we were out there, so you can imagine at the end of each working day, there's a spike in energy where people are wanting to charge their kit so it's ready for the next day. And that's where the prioritized demands come in, that they can turn the power off to some units at some times, and then during the middle of the night when everyone's sleeping, they can push the power to these areas here so they can be they can be powered overnight when there's a lower energy demand. But there's also kit which is left out in the field which has to run, and they use usually solar power to keep them running. On the left hand side there you can see one of the many weather stations they have around the station. This is 365 days of the year, it's monitoring the weather and recording it. There's a solar panel there to give it the power it needs to be able to record the data. And the batteries themselves, they last throughout the winter so they can keep recording throughout the year. In the middle there, you can see one of the solar panels which was out in the field for the science team I was with. It's a solar panel powering a battery, and the battery itself was powering a seismometer, which was looking at the rockfall on the mountains. So the solar panel kept the battery charged while it could during the summer months, and then for the winter, there was a voltage log in there, and you could see the slow decline of the battery, but the battery lasted throughout the season. it did help that the battery was in a insulated box. So you've got to adapt and use technologies where you can. And so what I can see, this was the crew, the station staff, and everyone who was there while I was there. The Princess Elizabeth Station shows that with the right frame of mind, the right integration of the technology, and it can be done there. You don't need to be looking at nuclear power or diesel generators to be powering stations. They managed to get, I think there was 45 people on site when I was there, living exclusively on renewable power. However, there is challenges, and the station still focuses, still has. To say it's a summer-only station, so people are only there between November and February. Ideally, it would be good to have people there all the winter, but the technologies they have, they don't last throughout the year to manage to sustain a staff. There is science which does go on throughout the year remotely, as you can imagine, for the winter months when you've got 100 days of darkness. The skies are dark and you've got clear skies. It's great for solar science, as I go back to what I was saying about the ozone hole and the aurora science which gets on there. So while I was there, there was a Japanese team installing us aurora camera, which will be recording throughout the year, throughout the winter months, and they'll be getting the data back at the start of the next season. The station itself is a relatively small station, so there's only a maximum of 50 people we're able to think. British Roller Station is up to 100, the Americans can go up to 1,000 people. And you've got to imagine, none of the other stations had this kind of level of technology in place when the station was conceived and built. So what the Princess Elizabeth were doing, this was the first time people were doing it. So, and they're showing that it can be done. And as you can imagine, technology changes very quickly. Throughout the design stage, I'm sure the technology moved on leaps and bounds between from design to implementation, and that's what they're doing. They're trying to keep up as they go along as well. So the new solar panels which they're putting in, they're putting new solar panels in which are more modern. And then the other thing is still whether, even with all your modelling of the station beforehand, whether it's still a big issue. You've got wind drift, which can build up on the solar panels. You've got ice, which is building up on the solar panels. So we've got to look at future technology, smart materials, which can maybe stop the formation of ice on them, and could they be used and implemented into the station? The other big challenge is transport. So what I said is zero emissions while you're living on the station. However, getting there, as I say, I had to fly to South Africa, then I flew on the large Russian Aleutian plane to the Russian base, that's the top left picture. Then I flew on a smaller plane from the Novo base to the station. And your main form of transport while you're on base, while you're doing your science work, is your skidoo, which is run on petrol. And there's a few Hiluxes as well, which is quite nice, a bit more comfortable than your skidoo for traveling around. But again, this is emissions which are being made, but that's the few emissions which they do have. There is the other option, transport of trying the old-fashioned way of cross-country skis. I did try that one day, of one couple of hours. I got about 2 kilometers from the station and decided that that was enough for me. I've got to take my hat off to all these explorers who are adventurers who travel across the continent on these skis. It's very hard work and it's very sore on your feet, and you don't get very far very quickly. So, just some lessons learned. For what I've learned, lessons I've learned from my time in visiting Antarctica and the research station. It shows that wind turbines work in Antarctica, and so do solar panels during the summer. They work in working the station, and they work for powering the science. What I found out, the scientists and the staff, they welcome the zero emissions credentials. The scientists thought they were going there, they were trying to just find ways of what's affecting the planet, and they weren't too negatively, adversely affecting the planet while they were there. And I think Princess Elizabeth has paved the way for how other research stations should look. The newer stations should have renewable energy systems built at the core of their design. If we go back to the South Korean station, that was built in 2014. That was 7 years after Princess Elizabeth was running. But they still hadn't learned from what they've shown can work there. Obviously, we still have the issues of the older stations. They can be retrofitted, be more energy efficient. That's obviously the big thing, push, is to get them energy efficient, and then you should integrate as much renewable technologies you can to reduce their emissions more. And I think Alain Hubert, this is Alain Hubert, the founder of the Prince Elizabeth Station, a Belgian Antarctic explorer, an Arctic explorer. What he says is, if they can do it here, we can do it anywhere. And I think that's really is the case, is that in Antarctica, we've got these harsh conditions. You've got brutal conditions of cold, wind, and weather. Here in the UK, we've got a relatively nice climate. It's very, we've got sun, we've got wind. We can do it there. We've proved we can live with no emissions in Antarctica. And why can't we do it here? And that's something which we really should be focusing on as an industry, as a community, and try and push that forward more. And what I just want to sort of round up is, look how far we've come in 100 years. Looking back right to the start, the maps which I had at the start, in 1912, the map on the left, that was what we knew as Antarctica. We kind of knew there was a coastline. It's not the shape we know of today. We didn't really know anything much further in from the coast, apart from the journeys which Amundsen, Scott and Shackleton, among others, did to the pole. But within 100 years, we've got, this is one of the high resolution models which gets produced by the science community of Antarctica. You can see we've got a lot more detail. We know a lot more of the processes which are happening in the continent. And we're using, the technologies we're using there, we can try and use them in everyday life around the world. And just a quick one at the end, just to look at the future and the energy in Antarctica. Things like, let's talk about transport. There is electric powered skidoos. So that's one way. And I know actually Prince Elizabeth are looking into buying a couple of skidoos to see how they work down there, the harsh conditions they have there. So that's one way of reducing power. But there is also the hydrogen is also seen as maybe one of the next big power usage storers or users for clean energy. Because it can be produced without a very low carbon footprint, and it can be stored well. It can be transported, and part of the transport means, say, as I said at the start, lots of the stations they use shipping to get their supplies in. Well, if you can use hydrogen in shipping, that will help reduce the energy use and the emissions which go on. And I say it's a clean energy source, and it can be renewed. So these are some just thoughts I just want to throw out there, just what ways we can do it there. So I hope that I've given you an overview of what Antarctica is and what the amazing work they are doing down in Antarctica at the Princess Elizabeth Station. I was very fortunate to visit there myself, and if you ever have a chance to go for scientific or engineering ways, I would definitely say take the opportunity. So thank you again. I see there's some things coming up in the chat there, so if you've got any questions, please put them into the chat and we'll unmute you and you can ask them, and I'll try and answer them best I can.
I'm the only one clapping because I'm the only one unmuted, Ross. But
Okay,
I'm sure
thank
everybody
you.
else is clapping in their minds. That was excellent, Ross. I enjoyed that, and it was well worth the waiting for and putting the jacket on. I'm going to try and do something clever here because we have a number of questions coming in, and I'm going to try and unmute the questioner and ask them to say the question. Ask the question directly. So the first one is Alistair McLean. You should be unmuted now, Alistair.
I am unmuted, Andy. Thanks very much. Brilliant presentation, Ross. Thanks. I guess the question is, you have talked about the modifications that you need to make to the wind turbines to make them function in Antarctica. Is the solar panels that are used, are they just the kind of ones that you find on the roofs of houses in the UK, or do they have to be specially adapted to?
So the solar panels, they're not specially adapted, and they're what you say you can buy off the shelf. Not you can really buy solar panels that easily off the shelf, but they are standard solar panels that you can use here in the UK as well. There's nothing special about them, and the technology which goes in them, it's just what you'd have in say the normal world.
Perfect. Thanks very much.
You're muted again. Caroline Hearn, I'm going to unmute you. Hopefully you're unmuted.
Am I?
Yes, I can hear you.
Okay, thank you. That was really interesting. I want to go there now. Get out of Jesmond. I wanted, are there, because it's there's so many nations involved. Are there any planning controls that, you know, influence what they're allowed to build there, and the fact that, you know, we hopefully don't want to build anything else there with a diesel generator?
There isn't actually any planning permission as such as what we recognise here in the UK. Obviously, there's the Antarctic Treaty, which dictates what you can and can't do with harming the environment. So you've got to adhere to that, but there's no strict, you can't just go to a book like you would in the UK and say, this is the encyclopedia of what you can and can't build.
Okay, all right. I just thought that would be, if they could build that into the treaty, that might help in the future.
Yeah, well, as I say, it's there's still about 20 years worth left on this current treaty, but obviously I'm sure the policymakers who are involved, key stakeholders involved in it, are already starting to look at what they want to improve. Obviously, there's the exploitation. People want to try and drill and mine in Antarctica, but that's one of the core, trying to protect Antarctica from those kind of explorations.
Right. Thank you. That's interesting.
I'm going to unmute somebody's name I can't pronounce. Is it Goodment? You're not unmuting.
Oh,
Hello, can you hear me?
Yes.
Hi, so yeah, it's Mark Good, but it just comes up because it's linked to my email address.
That's fine, Mark. I was wondering how I was supposed to pronounce that. You've got a very complex question, so listen carefully, Ross.
Oh dear.
No worries. Thanks for the presentation, Ross. It was really good. I worked in the Falklands as the petroleum storage depot manager, and we used to supply fuel to the BUZZ ships, the British Antarctic Survey ships. I suppose my question was: did you have a chance to understand the fuel supply chain down there? And was that exclusively supplied to the British via the Red Holes, or is there a fuels contract in place?
For the British, I'm not sure how the British work themselves, because I was actually there with the Belgians. But just for supplying fuel to the station, or obviously for the transport while there, it's usually shipped down. It's so while I was there, the Belgians had to go to the coast to unload a container ship which had some building materials, because they're building a new garage as well. And on that shipment, they had their fuel barrels, which are basically shipped down, and then they're using the piston bullies, and they basically have a tractor train to pull the fuel towards the station. Contracts wise, I'm not sure how that works. I'm not that involved. I'm not aware of how they work, unfortunately. But it's probably quite an interesting question how that does work.
Yeah, no worries. That's really, yeah. Thanks a lot for that. Much appreciated.
Thanks.
I'm just looking for the next person. I can't see them on my list. Got you, Peter. You have 2 questions. Could you ask your second one first? Peter?
Come on, just come in.
Well, I can read this question from the chat in here. You're saying, how are they dealing with COVID-19 as a whole? Yeah. Well, that is a very relevant question. While we were there, obviously it was in end of January and all of February, as the virus was starting to spread, at least grow in China and then start to spread around the world. It was a bit of a interesting time, because you're in isolation there. So some people have been in there since November. We've gone out in early mid-January, so before it started to spread. So you're there. You are in a bubble. You're in a sort of an isolated bubble. So it's a bit unusual. So all the people who are there who are wintering now, they will have been there since November probably. So they'll have been there before any of this started. So Antarctica is one of the very few places in the world where you probably won't see any cases of COVID-19. However, this next upcoming season, starting in November time, I think that's going to be a big concern of how they deal with that, how they manage that. Because obviously you've got people who've been there for over a year, and you'll have new people coming in who being exposed to it. So it's quite an interesting time for them coming up.
Peter had another question about the handling of waste, Ross. I take it one of the ways that's handled is by not generating it in the first place.
Yes, well, obviously they try to reduce as much of the production of waste as possible, of course, but there's two ways which they use the waste. Within the station itself, and they've got a waste management, a human waste management system where it's they got a bacteria which tries to decompose and recycle some of the waste, to clean the waste as much as they can, and they try to clean the water. They are improving the system as they go along. This season they were starting to work out if the water was safe enough to drink after being recycled. Obviously that's not the most appealing way of doing it, so they weren't putting it back in the system, but they were testing to see if that was possible. But any of the waste which is generated is stored on site, and then it's so when the ship comes in once a year, they unload the ship with all the stuff they need, then they load any of the waste which is generated, which can't be naturally decomposed, and that gets shipped back into, for this station anyway, it goes back to South Africa, where it then gets handled in an environmentally possible friendly way, recycled or whatever they can do with it.
That's good. Archie, I'm going to unmute you now.
Cheers, Andy. Rather embarrassingly, it's actually Ed, but it's named after my dog on my Zoom handle from a previous family Zoom call.
There's no answer to this. But if it's the Ed we're thinking of, we're not surprised.
Yeah, true. Ross, that was a really interesting presentation. Thanks, really enjoyed it.
Thank you.
And thanks to Andy and others for organising. Yeah, similar question to Caroline's, really. It was just, I guess, understanding how sort of future development is controlled or regulated, given that there's not really a single responsible body or government or nation that controls Antarctica. So,
yeah,
like, how, as you said, it is quite a sensitive environment. Appreciate there's not a huge amount of wildlife beyond the coastal areas, but yeah, how is that controlled?
Yeah, well, I think Princess Elizabeth is one of the anomalies with the stations. Nearly all the stations on Antarctica are government owned, so they're owned by the government of the nation, which they're run by. And the Belgian government do own a stake in Princess Elizabeth, but they don't own it and they don't manage it themselves. It's run by a private company called the International Floor Foundation. So a lot of the stations, they do try to follow their own governmental guidelines, because that's just, their regulatory bodies know how that is, and if it's government funding, they'll have to jump through their own hoops to match those in. But obviously, you say you've got the Antarctic Treaty, so other nations do hold everyone to account. So where I said no one just turns up on the station, basically all the stations are open to anyone, any nation. Even though it's a British base, the Americans can go there, the Russians can go there, the Belgians can go there. So you can't really lock a door. You can't lock it on and say, no, you can't come in today because I'm doing some weird experiment which could be detrimental to the continent. Obviously, back in the early 50s and the explorations and the initial Antarctic exploration days, there was some, I suppose, what we'd say questionable activities going on, but it is a self-managed process. So I by no way know every word of the Antarctic Treaty. So there might be some nuances in there which do try to regulate it a bit, but there's no big manual itself which says you can do this, you can't do that.
Mm-hmm. Okay, thanks.
We've got one question left listed up, and it's from Mark, and I've just unmuted you, Mark. That sounds like somebody trying to get their microphone working. Mark was asking about your route there. And you mentioned calling in Russia on the way past, or a Russian base on the way past?
So the journey itself from Newcastle, anyway, we flew from here to London, London to Cape Town, and then from Cape Town we flew to the Novo base. It's a longer name. I can't pronounce it. It's in Russian. It's called Novo. It's the main hub of that area of Antarctica. It's run by next to the Russian base, so they've got the big airfield, and that's basically a feeder airport for the smaller planes to go to all the stations which are in that vicinity. Princess Elizabeth themselves they are trying to develop a larger runway on site, so they could potentially have those planes coming in themselves. But Novo, it's a Russian base, which is where I went to, so that's where the confusion might be.
But so what's the point of going to South Africa and then going to, would there not be a base in South Africa? It's much easier to access Antarctica from there.
Well, so we fly. So you actually go through it. It's quite an unusual process. When you fly from Cape Town, you go to the main international airport in Cape Town, and you fly. You do any normal flight. You go in. You go to a check-in desk. You check in your bags, and you get a boarding pass, which is the most surreal experience, really, when you think you're going on this scientific mission. But the transport, the logistics transport from Cape Town into Antarctica is run by a company called I think it's Dromlan, which is they run the flights. And you've got to think of the distances which you're traveling. It's over 6,000 kilometers from Cape Town to Antarctica. It's a 6-hour flight. And considering it's 10,000 kilometers from London to Cape Town, it's more than half the flight to the UK again. So it's what some people get confused with on the distances. It's quite a long flight, so you need a big plane. And some of the stations themselves, they don't have the big runways, they don't have the infrastructure. When you're landing in Antarctica, you actually land on the ice. There's no tarmac runways. So there's only certain areas of the continent where they've got, I say smooth, semi-smooth enough ice where you're able to land these large planes onto them.
Rather you than me landing on the ice, Ross.
Yeah, it's we actually, when we flew there, just a side story. It took us 2 attempts to fly there. Our first flight wasn't on the Russian Ilyushin plane. We went on it was just a normal Boeing 757. Again, it's very severe. You're going to Antarctica on this normal airplane, which you fly about usually fly about. But we were halfway there, and they decided the weather conditions were not suitable for landing. So we got 4 hours into our 6-hour flight, and they turned us around. We got to the point of no return, and they decided that we needed to return back to Cape Town because it wasn't safe. So we actually had an extra 2 days in Cape Town because of the conditions. It really shows, even in summer when it's meant to be accessible, it's very hard to access the continent.
Well, we seem to have run out of questions, Ross. I'm going to apologise to everybody because this sounded like the old days when I was listening to Radio Luxembourg underneath the bedclothes, which I know there's at least one person on the call who's old enough to remember that as well. But it was excellent. It worked well. I think we've had a fairly good session. I'm now going to unmute everybody. And I'm going to thank Ross in the usual fashion.
Thank you.
Thank you. Brilliant.
Well done, Ross. That was great.
Thank you all for participating. And